Now we have a dynamic simulation of the process. However, it is not complete because we cannot reach stable conditions. The reason is that there are no controllers able to keep a constant value for flow rates, levels, and temperatures. We need to introduce controllers. In order to do this, we will start for the first one, which is the level controller for the reactor. We open the palette of the system, F4 in the keyboard. We go to the second group of blocks, dynamic and control. There are very different type of controllers, set point, split range, PID, DMC. The ones we are going to use are PID controllers, proportional, integral, and derivative action controllers. We introduce this one, for example, here. I close the palette, open the controller. I want to control the level of this reactor. In order to do this, I am going to act on the valve of the reactor product stream. When the level is too high, I will open the valve. When the level is too low, I will close this valve. I double click on the controller. I need to complete the two first tabs of this form. The first one corresponds to the connections. First, I need to specify the process variable, PV, the variable I want to control, the level of liquid in the reactor. I select here in the units the reactor, and of the multiple variables I can choose, I filter by the word level. There are still many variables, the aqueous level, the chamber 2 phase level. The two ones I am interested in are the liquid level and the liquid percentile level. The liquid level is expressed in terms of length, 1 meter, 2 meter, 1.5. I need to know the height of the reactor, but the liquid percent level, as it is expressed in percentual terms, it goes from 0 to 100, is easier to understand. I select this value. I am going to control the liquid percent level. Here I have the option to use a cascade control, selecting a remote set point from another controller, but I am not going to use it. I'm going now to select the output target, the OP variable, the output. And this is the valve in the reactor product streams. I select the valve in reactor products, and in this case there is a single option to select the desired position of the actuator. Select. I have already completed the selection of process variable and output. Now I need to complete the parameters in the second page. I will start by the tuning parameters. Kc is the proportional constant of the proportional action of the controller. Ti, the integral time for the integral action, and Td is the derivative time for the derivative action of the controller. The PID parameters of the controller. In order to provide the value to these parameters, I need experience to know which values are usually used for these ones, which are available in the companies when you work in them. In this case, we can use values from Aspen proposal. In the help system of Aspen, let me see here in the page of this part. No, in the class notes, moving from steady state to simulation, you have directions to go to this help part of the system. Here, this one corresponds to the reactor level controller. And here is, if you ask for help, F1, and you go to the parts HDS dynamics, control theory, general guidelines, choosing parameters, then you have a short description about recommendations for type of controllers and tuning parameters for the principal types of systems. I have already prepared in a file which is named choosing controller parameters a resume with these values. This page is available in Campus Virtual. Here in chapter 2 at the end, choosing controller parameters. And here you have a table resuming the main type of controllers: flow controllers, liquid pressure controllers, level controllers. In our case, we have a level controller. The mode of controller which is recommended is proportional or proportional integral. The derivative action is quite complex and you should be very careful to introduce a derivative action. If you use only proportional controller, the suggested value for the proportional constant is 2. If you are using a proportional integral, as it is our case, a value between 2 and 10, you must make a proposal in that range. And if you are using a proportional integral, an integral time between 1 and 5 is proposed to be used. In our case, we are going to use a value of 2 for proportional and 10 minutes, which is out of this range, but it's the value I have used for the example. So I go to the level controller. I am using a value of 2 for the proportional constant and 10 minutes for the integral constant. You can look at the status of the form and it says that there is an unknown range for the process variable. In the faceplate that we will show later to follow the behavior of the system, you have the representation of the process variable in the upper bar. You must select a minimum value, which is represented by the left side, and a maximum value for this process variable, in our case, the liquid level. In this case, it's very simple, because the level goes between 0% and 100%. This range is selected according with the expected variation for the variable we are using. For percentage level, it is usually between 0 and 100%. For molar flow rates, it depends on the range. For example, by default, we are going to use between 0 and double the value of the steady state. We will see later. Now we have completed, but there are still two values we must select. First one is the action, that by default is selected by HYSYS as reverse. The action is the way in which the controller must operate. For example, when the value of the process variable is above of the set point, this is the value we want to reach constant for the process variable, the action should be direct if the output goes also higher than for a higher value, or reverse if the action requires a lower value of the output. In our case, for example, with the process variable, the level of the liquid in the reactor, goes above the set point, goes above the value we want to reach, the output in the reactor products valve requires a higher flow rate. That means a higher value of the output. This means that a high process value requires a high output. That is a direct action. Okay. Finally, the mode of operation of the controller. By default, this is manual. Manual means that the controller is not acting. You can change manually the value of the output, the opening of the valve, but the controller does not calculate this value by itself. The desired value for the operation mode is, of course, automatic. This means that the system reads the process variable, compares this value with the set point, and determines, according with the tuning parameters, the output of the valve to correct this value. As you can see in our case, the set point is very high. I'm going to move it. You can do it by dragging the value, for example, to 50% height in the level. You can also change the set point here in the controller, 50%, or you can also change it here In the process variable bar, 50%. The light blue bar here represents the actual value of the process variable. As you can see, it is almost at 100%. The red arrow represents the set point, which at this moment is at 50%. The process variable is very high above the set point. The light blue bar below corresponds to the output, the percentage of the valve. It is of the 50%. Okay, now I am going to run the simulation. Let me close this. I'm going to place the faceplate here, close to the level controller. And now I run the simulation. As the liquid level is very high, the valve should be clearly open, close to 100%. Active. No modifications in the dynamic assistant. And it seems the system is not working. Let me check the integrator here in Dynamics, integrator. Okay, I need to modify the end time because the simulation is not running. We are at 5 minutes. I'm going to remove this value. This means that the simulation has a non-stop condition, and now when I run, no dynamic assistance, the valve is moved in order to meet the condition. And now the level of the liquid inside of the reactor has moved to the set point. You can see that it requires some time to move to that condition. So now we have the level controller working. We are going to move to the next controller. I stop the simulation. I need also a controller for the flow rate in the propylene oxide stream. If you open this one, the value of this flow rate is at this moment almost 4,000 kilograms per hour. So I'm going to introduce a controller to maintain the mass flow rate through this stream in 4,000 kilograms per hour. Again, open the palette. Let me see. Select dynamic and control. Take a PID controller. Open the controller. In this case, the process variable is the mass flow rate of propylene oxide stream. Propylene oxide stream mass flow. Okay. The output will be the corresponding valve, the valve for propylene oxide. I select the desired position of the actuator. I move now to the parameters tab. The value of the constant I'm going to use is 0.1. If we look at the recommendations table, for flow rate, the constant should be between 0.4 and 0.65. 0.1 is the value I have used. The integral time should be between 0.05 and 0.25. In this case, I have used 5 minutes, a very high value. The tuning parameters are not the recommended one in this example, and you should use preferable the values collected in the table. Again, the value will be between 0 and double the set point. The set point is 4,000, so I am going to select the maximum value of 8,000. The set point will be 4,000. And the mode will be automatic. Considering regarding the action, in this case, if the mass flow rate goes above the set point, this is, if the mass flow rate is higher than 4,000, the valve in this case should be closed. This is, for a high value, the output should respond reducing the value. So this is a reverse action. Open the faceplate and close the controller. This is the flow controller. I'm going to present this here. I run the simulation, no dynamics, and as you can see, the value is kept constant. If I increase the set point, okay, the system responds opening the valve and the flow goes progressively increasing to that value. And this is a slow response. I'm going to move the set point again to 4000, and here better, 4000. Okay. And now the flow is again reduced to that value.